Good afternoon, everyone. We'll go ahead and get started. Thanks for joining us for the final Wheatland seminar of this semester. We're really fortunate to have Dr. Nicholas Coops with us this afternoon. Appreciate the time that you've taken out of your busy schedule, especially this time of year with finals coming up next week and so on and so forth. Dr. Coops is a professor at the University of British Columbia and a Canada Research Chair in Remote Sensing. Prior to working at UBC, Nicholas worked in Australia as a senior research scientist at the Commonwealth Scientific and Industrial Research Organization. Nicholas is the head of the Integrated Remote Sensing Studio within the Faculty of Forestry at UBC. This is a research lab investigating and demonstrating applications of remote sensing data to environmental and forest production issues with graduate students and postdocs. He has published over 350 peer-reviewed journal papers and is the editor-in-chief of the Canadian Journal of Remote Sensing.
That's the best way to get your papers published, actually. Works in the best way. Be the editor of a journal that you publish in.
Right, well, there you go. Excellent. Let's welcome Dr. Coops.
Thank you very much. Very kind. Let's keep the applause to the end to see whether you think it's worth it. It's great to be here. It's nice to come across. Being Matt, I've never been here before, so it's a great pleasure. Part of the reason I wanted to come. Obviously, I think UBC has affinity with other strong forestry universities, and there's no question that this is one. So it's nice to be here, and thanks for the invitation. I know that there have been many speakers ahead of me who are more famous and intelligent than me, so I am grateful to having been included in the list. So I want to give you a sense of some of the work we're doing in the lab at the moment in remote sensing and its application to forestry. If you have questions, throw them out as we go. Easier than tracking back. I guess this is the boring topic, remote sensing of vegetation structure, function and composition. That's amazing. I didn't know remote sensing could do that. I think is a much, much better title to give us a bit of a sense about what we're going to talk about today. And I would be remiss if I didn't talk about the co-authors and the graduate students I have in my lab that really help contribute to the work we're going to talk about in this talk today. So the way I've broken it up is I want to cover four things. Four key technologies that I think are revolutionizing the way we use remote sensing in forestry. And I think we actually live in a golden era of using remote sensing in forestry. The technologies we have, the opportunities we have today are significantly better than they've ever been, as far as I'm concerned, in the history of remote sensing for the last 20 or 30 years. We're really at a precipice, I think, in terms of how we can use this data intelligently and how we can go away and apply it to real-world problems. And I think it's an exciting time to be a graduate student in remote sensing. It really is. And there are many, many opportunities I hope that you pick up on of how you might go away and use this data. And there's going to be four vignettes that I'm going to talk about today to give you a sense of how we're using it. So, forestry, remote sensing. I would be very remiss if I didn't start off by talking about, oh, I miss my beautiful, I'd be very remiss I would be very remiss if I didn't start by talking about LiDAR. LiDAR is simply the most sexy, revolutionary and important remote sensing technology that has happened in the history of forestry since photogrammetry. It really is a revolutionary technology that we cannot underestimate as in its power and the capacity for us to go away and ask questions that we've never been able to ask before. So LiDAR technology, as you probably know, stands for light detection and ranging. The reason I think LiDAR has been so successfully taken up by industry is that it's very, very simple. It is a simple analogy of an aeroplane, potentially a spacecraft, potentially a drone, flying along, sending out these pulses. The pulse travels at the speed of light in Maine, just like it does in Vancouver and Australia, and if we simply measure very accurately how long it took that pulse to come back from the ground, we get a very, very accurate estimate of the distance. So LiDAR is a phenomenally interesting technology to us because we get two things very useful in forestry. We get the terrain to a level that we've never been able to get before, as well as all the other stuff that's on top of the terrain that we would then think of as vegetation, biomass and structure. So we're getting two key attributes from LiDAR technology, the terrain and the vegetation as it lies on top. This is the space-borne version. We would love to have a space-borne version of LiDAR, proposed to Congress once, $1.2 billion it was rejected. So we don't have any plans for a space-borne dedicated satellite LiDAR system that is useful in forestry yet. The Chinese are talking about one. They say they'll have it up there by 2020. And we're putting a demonstration one on the space station. So we're getting closer to LiDAR from space, but really the majority of the LiDAR that we all talk about is from plane. 98% of the LiDAR that you will hear about or read about is from a plane. So the plane flies along, sends out the laser pulses, and from that we get the distance. We can scan backwards and forwards, and we build up this terrain map that's a very interesting surface of the terrain and the surface from these laser pulses that we get back. The laser pulse is in the near-infrared part of the spectrum. So very useful for us because it's very reflective from vegetation. There's a good wavelength for us to use. It's eye safe, so it's very safe for us to use. And we can get very clear penetration through the atmosphere because it's in the near-infrared part of the spectrum. We're starting to see multispectral LiDAR come into play. We're actually sending multiple beams down in multiple wavelengths. And we're hoping that different surfaces will reflect differently, which might give us some sense of more of an image-based application of LiDAR rather than just the point cloud as it comes back. So we've talked about LiDAR from an aeroplane. We know that it is airborne based. It's going to move this over here. We know it is airborne, and these different the technology that we use has a wavelength of around 1064 nanometers that allows us to go away and see the ground that we go through. So looking at LiDAR data, we get the ground. We also get all this information about the tree canopy itself. So this is a nice demonstration of what a forest starts to look like when we have billions and billions and billions of points. You can see that the tree structure becomes very apparent. We're starting to see the return of those laser beams on individual crowns. So we could try to go and find individual trees, or we can work more broadly across the landscape, what we call the area-based technique, where we look at larger plots rather than just individual trees. So going through with a pulse, this pulse is going to pass its way through, and then we get this distribution of those returns as we pass our way through the canopy. Now, anyone who knows PowerPoint would appreciate that this probably took me a very long time to do, so I sometimes get cranky when I don't hear gasps, not at the technology, but at PowerPoint, so I'll do it again. The pulse passes through, and look, we get these returns. So LiDAR is a very good technology. Obviously, we're going to get the ground return, and we're going to get this penetration of the LiDAR as it's passing through the canopy. The interest here now, of course, is, yes, we get the terrain, but here is all this biomass, this structure of the forest that we're able to go away and interpret as well. So LiDAR's been around since 1990s. Really, initially it was a profiling LiDAR. LiDAR originally used to be in one line, used to be for train lines and roads and power lines. The innovation that we talk about is scanning LiDAR. So we scan backwards and forwards from a plane or a drone. A plane will give us about a 500-metre swath, so we can fly backwards and forwards over the landscape, and we build up this landscape picture of the forest in terms of billions and billions and billions of points. The Europeans call LiDAR airborne laser scanning because they're pretentious. So we call it LiDAR in North America. The Europeans call it airborne laser scanning, but it's the same thing. So if you are doing research or you want to find out some stuff about LiDAR, then look up airborne laser scanning and you'll see a lot of stuff coming out of Europe. It's exactly the same technology, we just call it slightly different. So we've been seeing this technology used widely. It's really forming the backbone of what the Canadians call an enhanced forest inventory. An enhanced forest industry can mean many things to many people. It's like God. But you can see that different attributes are going to be predicted from an enhanced forest inventory, and that might be useful then in a management context. Here's one of the first LiDAR data sets that was collected in Canada. It's in Alberta. It's called Hinton. And this is an area here. It covers, where have I got the area, about 1 million hectares. It was flowing. There's a number of LiDAR acquisitions going backwards and forwards. And we do this sort of collection of plots. We then calibrate the plots with the LiDAR data, and that allows us to go and make wall-to-wall predictions of our volume estimates based on the LiDAR technology. This is area-based, which simply means that we group all those hits. We don't try to find every single tree. We simply group all the hits into plots, synthetic plots, if you like, 20 by 20 or 10 by 10 or 5 by 5 or circular if you want. But we take the relationship of all of those hits and we relate that to our plot data, and then we go and predict it across the landscape. Traditionally, our forest inventory might be more polygon-based. You can start to immediately see then what this type of product will give you is it's going to be a raster-based representation where each of these cells is a prediction of the variable that you want. In this case, merchantable volume, and then we can go and use that attribute then to go and make our predictions across the landscape. My whole talk is not about LiDAR, so I'm not going to go away and tell you how accurate LiDAR is, besides to tell you it's very, very, very accurate. It is a very, very accurate technology for giving us height, which is the way LiDAR was sort of developed. The rest of our relationships are based on models to give us volume, models to give us biomass. But we've been doing a number of studies in Canada that shows that if we look at our yield estimates based on the LiDAR prediction versus what is actually going into mill, we're less than 1% difference in the volume that we're predicting versus what's going in the mill. So if you have good models and good LiDAR data, you will get very good predictions of your volume. And you can use those to then go and plug those into a timber forecast model or use those in your planning. So we're starting to see Canadian companies invest in LiDAR. Now, Canada has a unique forest industry to some extent with a lot of crown land. There are issues about companies wanting to invest in LiDAR given the land is actually not theirs. So it's not necessarily a given that every single company in Canada is willing to invest yet in LiDAR. So in Canada, we sort of see these government companies partnerships to try to purchase it, where the government recognises that there's sustainable timber management value, that the DEM is useful for other applications, and the company is able to go away and use that LiDAR as part of their management structure. So I'm sure I can convince you that LiDAR is fantastic for forestry, because most of us probably know that already. We're doing some interesting work on other ways to use LiDAR, and I mentioned this before when I was here, that I actually think one of the key benefits of LiDAR is the terrain model. And thinking about the terrain model in other ways, as it's been produced from LiDAR, I think is another useful type of way of thinking about LiDAR data. So this is a study area at the north of Vancouver Island. So Vancouver Island is the big island next to Vancouver, so on this map I guess Vancouver is going to be here. This is the northern part of it, so it's very productive forest. And this is an area of forest that BC Timber Sales, which is a quasi-government timber organisation in Canada, British Columbia, and Western Forest Products, who's a private company, they have started to fly LiDAR over their holdings. And we're starting to look at that LiDAR data in different ways. For the forestry aspect, we're looking at things like site index. So yes, we can predict the current volume, because that's what the points are reflecting off. The other thing we can try to predict is something like site index. Site index is a little bit more difficult for us to predict directly because site index is how productive we think the stand would be at a certain age. So what we can try to do, use LiDAR in that context, is we can work out our height, but instead of looking at the height of every single tree, we go and try to find the height of the trees in some sort of regular grid. So here you can see we've got a 10 by 10 metre, no, 100 by 100 metre grid that we've put over the forest stand, and there we go and extract the tallest tree that we have per hectare. And then we can actually plug that value into some sort of model that then allows us to go away and generate something like the site index. So we can get beyond just the standing volume and move into other metrics from LiDAR as well, like site index. If we combine that with age, then we can start to get a bit of a sense about how accurate, how predicting our site index is likely to be for these stands. So here's just an example of some young stands. We're getting our dominant height that we can see from the LiDAR. We know what our age is going to be from the inventory, and then we can take 1 in every 10 trees or 1 in every tree per hectare, and we can start to build what we might characteristically think of as some sort of site index curve. This is useful because often in British Columbia, our site index curves for our young stands are actually quite poor. We don't measure the young stands very much, and the young stands are growing under different climatic conditions than they were 100 years ago. So I do think LiDAR has a capacity to scan the landscape, pick out these key site index trees, go back and look at age, and then allow us to go away and build up these types of curves. Another way we're using LiDAR data is at the sort of the broader scale is to try to get to individual trees. So you can imagine this point cloud coming down. As this point cloud comes down, some of the points are going to hit trees, and it's going to go between trees and between the sides of the trees. As a result, it's very difficult with LiDAR data to find every single tree every single time. I know some companies want to. JD Irving is passionately trying to invest in technologies to go and find every single tree. But it's complicated, as we all can imagine, because it's difficult to find every single tree routinely and accurately, especially if the trees have got different sizes, and especially if you're in a multi-age stand where you've got one tree under another. So plantations and planted forests have probably got much more chance of finding individual trees than in more mixed age, mixed species stands. So rather than forcing ourselves into a mentality that says, I've got to map every single tree, another way you could try to do it would be try to downscale to give us the trees. Now, Chris Hennig has been doing work at UNB. They do a nearest neighbour-based approach to try to do this. We do a curve-fitting approach to try to do this. So for every plot, we have simply a distribution by stem number or by volume or by DBH, whatever you like. Here's just the distribution of the trees in each plot. We can fit curves to those plots, and then we can use LiDAR to predict the curve. So we don't use LiDAR to count every tree. We use LiDAR to predict the curve, and then from the curve, we can then go and estimate this is the range of trees that you would have within that plot and the size of trees that you would have within this plot. So again, another interesting way of using LiDAR, not forcing us to count the trees, but still allowing us to go away and see this individual tree-based information that might be important for growth models, might be important for our types of management that we do. In this particular graph, you can see the blue lines are the distributions of the trees from the plot, and the green dotted line is the LiDAR prediction of what the distribution is of trees in that plot. So LiDAR is good for forestry. I also said, though, that LiDAR is good for the DEM. So we're trying to play with the use of LiDAR to look at riparian, habitat, and fish. So the DEM that we get off the LiDAR is extraordinary. Beautiful patterning. We can see the stream network starting to form. We can see slope and aspect. And foresters use this for trafficability and slope and information like that. But we can also use it for water. So we could pour a bucket of water over the DEM and we will get a very, very accurate network of streams. And we actually get the stream network from LiDAR, the smaller streams, much, much more accurately than any other technology that we can use. Because photogrammetry-based contours are mainly based on the top of the canopy. It's very hard for them to see the small streams at the top. So LiDAR actually gives us a great sense of where we are in the stream network. So here you can see is a LiDAR-based prediction of the streams. This is not from a stream map. It's what LiDAR says the streams are based on putting a bucket of water on top of the landscape. And you can see that we're predicting streams all the way up to the very top of the ridge lines, rather than a contour map that may actually start the stream there. This stream network is very, very accurate from LiDAR because the DEM is very, very accurate from LiDAR. From that, we can go and do a number of computations. One is work out stream order. So now that we actually have a very accurate map of all the streams, we can then go and work out the level of streams. So that's predicting the stream order based on LiDAR data from the DEM itself. And we can compare that to what the province says. The yellow is the province's streams, the blue is the LiDAR streams. So you can see the province just doesn't have all this information about these higher levels of streams, and in some cases, their streams are completely wrong. That's because it's a very forested environment, a very intersected, sort of transected environment, and it's all covered in forest. So we wouldn't expect their techniques to be perfect. The LiDAR is certainly giving us more information than we've ever had before. I can take my network of streams and I can look at the slope of every stream. So I can break the stream into segments and then I can look at the slope of every single stream segment in the network. So I can then map the slope gradient. And this is what's interesting in British Columbia because this is the direct predictor of salmon. Salmon cannot go back up the stream if it's too steep for them to swim. So suddenly every single stream then we have a salmon rating of how likely we think it is to be able to support salmon based on the stream slope as we go back up the mountain. So here we can then predict for each stream the stream gradient, the potential accessibility of that stream for fish, as well as information about the stream class. We can also predict, because we have the trees, the canopy cover, so we know how warm the stream might get. We know the sinuosity of the stream. We can work out how high the vegetation is around the stream. We can work out how much sunlight on a daily basis hits the surface of the water in the stream. So we can start to build up this network of this database of extra information about riparian zones and the functioning of riparian zones and their likely habitat simply based from the DEM. So to me, this is an exciting area. If I was a master's student and I was starting my master's, I would do my master's on fish, DEMs, and LiDAR, or anything to do with riparian zones and LiDAR. I think it is an understudied area that is tremendously valuable and important. The LiDAR we've been talking about is Hottotrot LiDAR. So the LiDAR I was talking about for Western Forest Products was 12 points per metre. So that's an extraordinary density of LiDAR data. It's not the best we can get, but it's pretty cool to have 12 points per metre. But that's only a small area. But today, we're starting to see large state-based mosaics of LiDAR data. And I know that the US is flying state by state by state by state. The closest we have is Alberta. So Alberta is, well, it's there. It is a part of Canada. Here it is here. They have a lot of money in it. They used to have a lot of money in Alberta. And with all that money they used to have, they actually spent quite a lot of LiDAR data. So a lot of this area is being, there's a lot of gas exploration. There's a lot of forestry activity. So what happened was, over the years, these companies purchased a lot of LiDAR data. So the government came in and said, we will purchase the right to use that and we will fill the gaps. So it was a remarkable insight of the provincial government about 5 years ago to then produce this LiDAR coverage. So this is Alberta, this is the Rocky Mountains, this is flat Canada. And the area that's covered is essentially the forested part of Alberta. There's some gaps missing there. National parks weren't flowing, for example. But at the time, it was the largest single area mosaic composite in the world. So it's a tremendous data set to go away and use. It has lots of problems. It has different densities, flowing at different times, by different operators, with different LiDAR systems. But don't let the technicalities blind you to forgetting that this is a LiDAR coverage of the state of Alberta. It's extraordinary, province of Alberta. It's extraordinary to go away and think about how you might go and use that. And I think this is where we can start to think about large-scale mapping of LiDAR. We couldn't do this 10 years ago because people were still buying postage stamps. But now we're at a point where we can do wall-to-wall mapping. So here's just some subsets of Alberta. This is the P95, so this is the 95th percentile. Essentially, it's height. So you can automatically start to see across the province, of course, the vegetation has lots of different heights. But look at this beautiful pattern. This is the forest harvesting that we see go on. We see the riparian zones, we see the management, we can see oil and gas. All of this is reflected in the structure of the forest that we can see. We can go other metrics as well. This is the variation in the hits. So rather than just taking the top hit or the cover, how many hits, which is my next slide, this is the variation of the hits. So a big old stand that has lots of structure is going to be higher, redder. A stand that's very simple is going to be blue. So suddenly not only do we get height and cover, we get structure. We can combine these together to go and make these types of maps. We've never had these before in the history of forest ecology. So this is structural maps of the entire forested area of the province. We can understand the height, the cover, the structure. The biodiversity value of this is very, very significant because we can map then where we expect certain species to be. This is just displayed in different colours, where different colours will highlight high cover, high structure, high height. We've been using some bird data. So this is then the predicted bird richness. So this is the 3 LiDAR metrics on top, height, cover, and variation. And there's a couple of temperature metrics. If we combine these together, we can then go and predict overall bird species richness. We've never been able to predict this type of variable for having these structural metrics. We can do it with climate, we could do it with Landsat, we could do it with leaf area. We've never been able to do it with structure. So if I was a master's student, and I was studying my master's here at the University of Maine, I would be thinking about using a statewide coverage, and I would think about correlating it with eBird data, and I would do statewide maps of species predictions of different birds. We can also look at the patterns. So here is a simple way of thinking about what I've just said. There's a forest, it's got different heights, different covers, and different structures. So I could actually make a map that classifies Alberta by these structural types. So this is a statistical clustering. I take every single pixel and I cluster them all and I come back with a map that tells me this is the 8 most common structure types we have in Alberta. And this is the point clouds of what they look like to visualize them. There's some very low, dense canopy, some very open, taller canopy, some moderate, dense canopy, and so on. This will be a function of species, age, disturbance, history, management, all encapsulated in these different classes. And then I can map the classes. So then I can produce a structural classification of the map using all of this wall-to-wall LiDAR. And I could go and compare it with something like Landsat. Landsat's going to be giving me my species perhaps, or if not my species, it will give me a broad biome classification, coniferous or broadleaf or mixed or something like that. And I can combine it with my structural information that I'm going away and getting from LiDAR. It's incredible. So I know the data is crappy. I know it's 1 point per metre. I know some of it might have been collected in 1986 and some of it might have been collected in 2004. But putting these together to give us these statewide layers and using it in this broader context, I think is exceptionally valuable. And we're not doing it enough. We should get off the train that keeps saying 5 points isn't good enough. I hear someone's flying 10, and then tomorrow it will be someone's flying 20. J.D. Irving's flying 20. New Brunswick is flying 30. Then suddenly we go, oh, I'm not going to waste my time with 5 points per metre. Are you kidding? This stuff is fantastic. So I would try to think about, don't get caught up in the hype of saying you need denser and denser data. The LiDAR data itself is extraordinary. It doesn't matter how you slice and dice it. We also do work with LiDAR data in urban areas. So actually in Vancouver, the best LiDAR data is owned by the cities. They use it because they get extraordinary 3D maps of the city itself. I did not know. But when you plan to build a building in Vancouver, which is happening all the time, if you've been to Vancouver, the plan and what actually ends up there are not exactly the same. The building might have a few extra little things or minus a few little things. And so the city actually doesn't have an incredibly accurate map of what is there. They have the plans and they knew it was supposed to be there, but it might be missing something. So they actually fly LiDAR to give them 3D building reconstructions. So this is phenomenally valuable data for the city. It's inclined to be quite dense. The thing that we can ask for that is then urban vegetation. So urban forestry has taken North America, the world by storm, North America by storm. We have an urban forestry undergraduate program though. Now, our fastest growing program, it's got 60 undergraduates in the first year, 80 undergraduates coming in the second. So it will be our second largest program in 2 years. So urban forestry has become enormously popular. And every city, like Vancouver, is obsessed about being the greener city. So this idea of linking where the trees are and mapping the trees in a LiDAR context is very, very useful and attracting a lot of interest. This is just a LiDAR point cloud of the city, or the suburb. So we can easily see the tree structure. We can actually easily see whether it's coniferous or broadleaf. And then we also have a very good description of the buildings themselves. So the work we do is we actually map buildings for solar panels, but I'm not talking about that now. We also map the trees. So we have LiDAR coverages for the entire Vancouver metropolitan area, and we go away and use the LiDAR data to map every tree. The reason the city cares about this is because the cities are spending tens of thousands of dollars planting trees, and in a lot of cases, the trees are dying. So they just plant a tree, they don't really think too much about the watering of it, they don't think too much about the soil, and as a result, a lot of the trees that we are planting in our cities are dying. So they're becoming concerned about that and would like to do more of an inventory about how healthy the urban trees are in the city. So this is a great application for LiDAR. Our case study here is Surrey, fastest growing city in Canada. It's the suburb or big city that's south of Vancouver. This is Seattle just down here. So this is quite a large area. They spent $80,000 a year watering their trees. So if they had any sort of map or comprehensive idea of how accurate, how healthy the trees were, they'd be very keen to know how to do that. So we took an approach of using LiDAR data, flew the city with LiDAR data, and then we mapped every single tree. So mapping every tree in an urban context is relatively easy because the trees are inclined to be by themselves, or at least separated. They don't really have another tree under them. They're sort of in a simpler geometric environment than a forest. So it's relatively easy for us to count them. We can also do more fancy stuff like work out their height, work out their width, and we can work out their density. So we can actually use the city's database about what they planted and when, and we can use the LiDAR database about where exactly the trees are, and we can link those together to go away and give us an urban tree height index. So what this is the tree age, that the city told us where they planted it, when they planted it, and LiDAR is telling us how tall it is. We can then plot it this way, and then we can come back and say, for some reasons, these trees, you do this by species, so this might be cedar, all of these trees are shorter than they should be compared to the other cedars that we have in the environment. And this was a metric then that we then plotted over the entire city to tell them whether the trees were smaller or taller than we thought they should be for their given age. Now you could do that for height, which it is here, but you can also do this for canopy density. Trees that are very open, trees that are very closed. This doesn't necessarily mean that the tree is dying, but it certainly means that this tree is going to be under more stress. That could be imposed by another tree, it could be because the drainage is terrible. At least it's an initial map that they can use to go and study the trees better to work out what's going on. LiDAR in urban forestry is hot, 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 hot. If I was an undergraduate, I'd be working on, a master's student, I'd also be working on that. So I sort of see LiDAR as, well, it's phenomenal. So half the graduate students in my lab are still doing research projects on LiDAR. So, you know, not every single question has been answered. Some questions have been answered. In many cases, LiDAR is an operationally accurate, usable technology. But there are still other questions that I think are relevant. And there are still other questions that are being asked. So it is still driving, however, a lot of the research that we do in the forestry community, and I think will for the next decade. Okay. That's for an aeroplane. I want to talk a bit about spacecrafts now and using remote sensing from spacecraft. A very cool NASA video. All the cool videos of NASA. And one satellite which has really become, well, an inspirational data set that we can go away and use now is the Landsat series of satellites. So Landsat originally launched in 1972. We're now on to Landsat 8, which launched in 2013. The longest record of satellite data we have in the history of the world. At the moderate resolution. AVHRR is slightly longer as a broader scale, but this data set is unique in its capacity. Let me tell you an old story. When I was a master's student, I had a project that my supervisor had organised for me, and it was on lake salinity. And my supervisor bought me one Landsat scene. Reagan was in power. Landsat was 6,000 Australian dollars for the Landsat scene. So my supervisor counted his coins, broke the piggy bank, sent it off to the US, and then came in with the tapes. The tapes were 6 tapes high as they walked them in. When it came in, there were actually trumpeters. As my supervisor walked in the tapes, they were so fragile. I was a nervous wreck picking up that tape, shaking like this, putting it on the thing. And I went away and did my analysis. It took me, well, it took about 6 months from the time a Landsat scene was collected to when it arrived in Australia, and about another year by the time I'd finished processing it. And I was actually looking at sediments in the lake, which by then had completely dried up, and the lake was now a salt lake because there was no longer any water in it. So perhaps a good example of costly, expensive data, very hard to get hold of, which really held back the science. And so I would argue that in the 80s and the 90s, Landsat was an underutilised resource because of these huge constraints. But as most of you know, Landsat data became freely available in around 2007. So interestingly, in the first month that the Landsat archive became free, more Landsat data was downloaded than had ever been purchased in the history of the Landsat program. So the idea of free and open data that everyone can go away and use massively expanded people's interest in Landsat. And it's revolutionised the way we think about Landsat, because now it's not just one scene that I get for my study area. We now have hundreds and hundreds and hundreds of scenes that I can go and get if I wanted to, because I'm not paying $6,000. So here's a map from the USGS, and we can start to see some parts of the world have over 1,000 Landsat scenes that have been collected through the history of the Landsat program. So this is extraordinary. And what it allows us to do is completely rethink the way we process Landsat. So in the old days, we used to have before and after, because it's all we could afford. And we used to subtract the two of them, and that gave us the change. So this is the old way we used to do it, because that's as many scenes as we used to have. Maybe you were lucky and you had 3 scenes to do your change detection on. But now, if I have every single scene ever collected over the history of a Landsat archive, I no longer have to think about scenes. I no longer have to think about plots of land and big squares and downloadable chunks. I now can simply think about a pixel, a 30-metre piece of ground, and I can think about the history of that pixel for the last 35, 40 years. It completely changes the way we think about doing our Landsat processing now, because everything comes down to the pixel, and it's simply the history of that pixel through time. Here's Saskatchewan. It's somewhere in Canada. I never really have been there. I fly over it a lot, but normally on my second Chardonnay, so I don't really look down on it very much. It's a province in the middle of Canada. It's very flat, and here it is here, and you can see this is a Landsat mosaic of Saskatchewan. But the reason you cannot see squares of Landsat data is because we've compiled this from Landsat scenes. But you don't think about scenes. You simply think about the pixel. Is the pixel cloud-free? Is the pixel close to another pixel that had cloud? Is the pixel near a bit of error? Is the pixel at the wrong time of the year? So I can sort of sieve all of my options, and I take the best one, and I make the mosaic from the best pixel. So we call this the best available pixel composite. And this is now the way we think about Landsat data. You don't think about downloading a scene anymore. You think about the pixel and how the pixel has changed, and then this is the map of where I got the pixel that went into this mosaic. So this mosaic was made up of hundreds of Landsat scenes, each contributing a pixel, or 10 pixels, or 100 pixels to the overall composite. So this is really very interesting because it gives us these much, much better high quality mosaics that are very clean in terms of their processing, because we're able to pick the best pixels that we want to. Now we'll still have, this is for 2000, so we'll still have some errors, we'll still have some cloud, we could never get a good pixel. We still might have some errors, but it also becomes quite easy to clean. So here's a mosaic, but here's some problem areas. Has some data gaps, we have some cloud that hasn't been properly screened, a bit of haze that got in the way. This is one of our scan errors on one of our Landsat. So these are attempts to be a good mosaic, but they've still got errors. But because I can then use every single pixel throughout the entire record of the Landsat archive, I can then go away and think about how that pixel is changing, and suddenly events like noise become very, very easy for me to go away and see. So it's no longer a two time step, and if there's change, is it real or not? Suddenly we're getting very accurate estimates of that pixel through time, and any change we can then look at and say, do we think this is an atmospheric change? Do we think this is an error? Or is this a real change, such as in the case of fire? So we're really changing the way we process Landsat data now by thinking about these pixels and how these pixels change through time. So here's just an example of mosaics. I've tried to do the best I can, but 2004 was pretty bad, 2005 glorious, but there was a fire. 2006 couldn't get any data, 2007 pretty good. I can have some logic, I can fit every single pixel through a trajectory, and I can go and find all that noise and then produce composites, which I can then go and do my change detection on very accurately, resulting in this. Now the next thing I'm going to show you is going to be extraordinary, so I want to hear a collective gasp. The most important part of this is actually cut off the screen. 73,544 Landsat scenes. This is an annual mosaic of Canada that we've produced from 1984. It's been done to 2016 now. 30-metre resolution. I could zoom in here, 30-metre resolution. There is no cloud. There is no noise. This is a reflectance-based product made of 73,000 Landsat scenes. So we're able to do things we've never done before with Landsat data, to go away and look at these types of environments, and then go away and look and try to see at the change. That's the change in Canada. So massive fires in our north, massive fires in the boreal, all by year, all by shape, all by size, and in the south we have all our harvesting, all by year, all by shape, all by size. Some geography, New Brunswick, private landowners, small lot owners, we can see the patchwork. Alberta, Manitoba, huge fires. Uncontrolled, we don't go and fight these fires. If there's no people at risk and no property at risk, they're allowed to burn. They're a natural part of the ecosystem. We can see these massive fires coming in. Look at the scale difference, it's the same scale. Alberta, the poster child of damaging your landscape. We can see here the cut blocks, the pipelines, the oil and gas exploration. We can see the attempts by the forest industry to naturally emulate fire by doing the patchwork that actually builds up the fire scar. So we can see all of these patterns come through on the Landsat archive. All of this data is publicly available, which we can go away and use. It's very accurate by year. So when we say it's a disturbance, we are right in 98% of the cases. If we say it's a stand replacing disturbance, we are right within 98% of the cases. If it's been cut down, we can see that. If it's been burnt, we can see that. Now, insect, disease, things that defoliate the canopy a little bit are less obvious to see, and Landsat will have more trouble with the trajectory. And then you need to have you won't be classing it as simply fire and harvest, but you'll be going away and classing it as other variables that are perhaps other attributes that are perhaps less accurate than the disturbance itself. So, Landsat gives us the history. But then you said, what about LiDAR giving us the structure? Well, this is a cool way of using Landsat to give you the history and LiDAR to give you the structure. Two stands, one that's been burnt and coming back, one that's natural or unburnt, if you like, regenerating. We can go away and look at LiDAR data, but we can use LiDAR data along a strip, but then use Landsat to tell us when was that stand disturbed. So we know when it was disturbed, and then LiDAR tells us what the current structure is. So we can actually get these types of ecological predictions that we've never really been able to sense remotely before. So this is two variables, cover and height. This is a chronosequence, but not a true chronosequence. This is a chronosequence by us going to different stands of different ages. We go to different stands of different ages based on the Landsat. LiDAR's giving us the structure. So we can see a stand prior to fire, and then we can see the effect of fire as that stand ages and recovers following the stand. The interesting thing here is look at the effect of the standing wood. So even though the fire has come through, there's still lots of standing timber, which the LiDAR still sees. So LiDAR's giving us this stand structure that's still there for almost 10 to 15 years after the fire. Then you would see the stand being perhaps as short as you would think a stand might be following fire. So interesting in terms of the biomass and the sort of the partitioning of that biomass after fire, we're actually able to see that very accurately using the LiDAR response. Height is this one and cover is this one. With cover we see a much more dramatic loss. So the fire burns the cover disappears, we have much less cover, but the height of the forest is still there following the fire. We can do this with simple LiDAR metrics like cover and height. We can also use our fancy pants LiDAR metrics like proportion of clumps. And again, look at different fires at different ages, at different heights, and go and try to see how is that stand changing at different vertical levels. So this is the understory in black, so we can see that the fire burns, and then as that fire starts to recover, it's the understory that comes in strongly, then the different other parts of the canopy start coming in as that forest comes back. Extraordinary. So merging of Landsat and LiDAR, a great research area. And I think bringing these technologies together is an exciting thing to think about in terms of how we think about the forest and change. Because remember, LiDAR is inclined to just be once. So sort of bringing in this history from Landsat I think is really cool. Okay, going back to Alberta, we actually do quite a bit of work in Alberta at the moment with bears. So grizzly bears are not threatened in British Columbia. In fact, we've just got rid of the hunt, which was announced by the new left-leaning government 3 months ago. Because we still have a hunt, allowable hunt, whatever you call it, on bears. On the Alberta side, they're threatened. So you can't hunt them on the Alberta side. On the Alberta side, this is because the bears have much larger home ranges, they're smaller, and there are fewer of them, and that's because they can't eat salmon. So the salmon on British Columbia is coming down the rivers. The bears have a significant amount of salmon and protein through the diet. On the other side of the Rocky Mountains, there's no salmon in the streams. So we have bears that don't aren't able to rely on fish to get their protein. So you get smaller bears and bears that have larger home ranges because they need to go further to get the calories that they need. So there's a lot of interest in Alberta in general thinking about bears because this is the same area where the oil and gas is. This is the same area where the people are. This is the same area where the Rocky Mountains and Banff is. So there's a lot of pressure on this foothills area of Alberta, and yet this is where the bears are as well. So it's interesting to think of a remote sensing perspective to this. For their diet then, the bears rely on berries. So the bears eat lots of berries and vegetation and roots. They do eat deers, small babies. They do eat protein when they need to, but they are very linked to the vegetation. And there's been some concern that with climate change, the sync between when the bears come out of the den and the availability of the vegetation they want is becoming uncoupled. And so really it's around how can remote sensing be used to look at vegetation, phenology, the bearing event, the fruiting events, and where it actually falls within the landscape. Here's just an example of a bear's diet through time. And we can see that a lot of that, this is only the vegetation part, but we can see a lot of that vegetation part is linked to the roots and the berries and the fruits of the vegetation that it's going to go away and try to eat. So we want to try to measure these from remote sensing. This is tough because these are small. So a berry is small. So using a 1 kilometre by 1 kilometre pixel is very difficult to go away and use broad pixels to look at this. So we actually use these things called phenology cameras. So these are cameras that we mount on trees, and they look out at the landscape, and they take images that we can then go and process just like we pretend they're in space. Why is this one black? Because people in Alberta are crazy. They shoot anything. So if I have a beautiful white unit, like it was when I bought it, and then I put it there, I come back, it's going to be in 5 pieces a day later. So I paint them black and put them very high up on a black tree. Then I have a very big sign that says UBC study area over there, camera over here. So these cameras are in the trees, and these cameras take a picture every single lunchtime. This is a year worth of phenology camera imagery, which we can then go and think about. How is the understory responding to climate or during the year? How is the overstory responding to the climate during the year? This is a test case. This is actually the site we focused on. It's a bit wider. And the particular berries that they like are a purple flower. So you'll see a purple flower pop in and out. That's the vegetation that we care about. So this is one of our study cases where we sort of plotted out the area when we put the camera in. We've got a fair idea of how big that land is and sort of what proportion it is. What we do is we actually go away and take every single image. The images are taken at lunchtime, but even though they look really contrasty to you, they look like they're jumping around a lot, if we actually just put a grid over that entire image and then we start to play with the bands, spectral bands, in each one of those grids, we actually get a pretty uniform signal. We certainly get a very uniform signal when there's snow, and then we can see the phenology come up, we see the growth of the species, and the phenology fall back down again. So we can use these images over time, and we can process them to give us this. This is the amount of greenness of the landscape based on the camera. So we can start to get a sense of where is the vegetation healthy, where is it not. And here's an actual trace of the particular species that we care about. It's got a purple flower. We can see there's snow. The species greens up. When the purple flower comes up, the greenness actually becomes purple. So we don't see green anymore, so it falls into greenness, peaks up again after the flowers have fallen off, and then goes away and falls with snow. So we actually track each pixel through the year, look at its curve, and then come back and say, okay, we think that is the species that we care about. Hedicerum, for example. So then we can make a map and say this is the green up date of the species we care about, this is the green down date of the species we care about, and then actually map every pixel that we believe has the presence of that species in the landscape. So this is useful then, because then we can say this is the carrying capacity of this patch of land for the bear. So I never actually saw a bear. I saw my fat postdoc bending over one time when the camera went off, but, which I thought was a bear, briefly. But we never actually saw a bear, but we're not trying to see bears. We're trying to see the landscape and how it changes, and we can use this information to then plug into a food model that then a bear ecologist can use to go away and think about how the landscape is changing. We've got 20 of these cameras installed permanently, so for the last 3 years, over Alberta along this transect that tries to cover the main vegetation groups that we expect for the bears, and it's allowing us to produce these types of proportion of landscapes of different species, proportions of flowers, proportions of roots, that then give us a bit of a sense of the diet for that species in time. Running out of time, I do want to finish by talking about drones and how we're using those. Drones are perhaps the most overhyped and useless technology that we hear about a lot with remote sensing these days. So I would be very careful about drinking the Kool-Aid about drones. You know, they are so limited. So limited. So you want to fly the forest in British Columbia, you have to always be able to see the drone. That's a problem. The thing can only go for 20 minutes. That's the problem. We can only fly 3 hectares. That's a problem. So don't start thinking that there are going to be swarms of drones flying over the Canadian landscape collecting all this phenomenal data. They are technologies that are very useful for certain applications, and I think if you are going to work on drones, then keep your topic nice and narrow. Keep your topic narrow and focused on why drones are good. This is a drone taking a picture of a drone. This is why we like them. I'll do it again, because this is another This is a drone taking a picture of a drone. Incredible. It's also in China, where you can fly drones wherever you want under any circumstances you like. So this is where we're doing a project in China looking at drones. But drones are extraordinary in terms of the detail that we can get. So they're operationally constraining, but the detail that we can get from drones is absolutely extraordinary. We can try to put a LiDAR on drones, but that's right at the edge of what we can do today. LiDARs are heavy. LiDARs are expensive. You're not going to put a $90,000 drone on a $90,000 LiDAR on a $250 Flybe drone you bought from Radio Shack. So you need to get your math right to work out how you might go away and use a drone on a LiDAR. The way we play with them, and the exciting thing, is digital photogrammetry. So digital photogrammetry is where we take hundreds and hundreds and hundreds and hundreds of photographs, we feed them into a computer, and a computer does photogrammetric techniques. So it matches every individual pixel on every single scene and gives us a 3D point cloud. Hundreds and hundreds and hundreds and hundreds and hundreds of photographs. These photographs have exceptionally high overlap, which then allows the same point to be seen on lots of photographs, which then allows extraordinary amount of detail. So this is where the revolution is. Drones are cool because it gives us the platform. Digital photogrammetry is cool because we've only had the algorithms to do this in the last 5 years. Normally, what a photogrammetric tools will do is they pick an object. I can see a house, I can see the house, I can see the house, let's find the house. Digital photogrammetry, every single pixel on the photograph is matched. Every single pixel on the photograph is matched. So we get these extraordinarily dense point clouds that allow us then, extraordinary dense point clouds that allow us to go away and see the landscape. Google Earth. Drones. So I'll do it again. Google Earth imagery, which we think is extraordinary. That's from a drone. So it's extraordinarily detailed data, and by looking at these points in three-dimensional space, we can simulate the stand within 1 centimetre by 1 centimetre voxels. This is a model of the forest based on the points that we get from the drone. So we are getting extraordinary data that's actually quite similar to LiDAR, because it's a point cloud of billions and billions of points of the forest. Now, the issue with DAPs in general is that we cannot see the ground. So if I compare a point cloud from photogrammetry with a point cloud from LiDAR, my tree heights at the top are going to be very accurate. But as I get lower and lower and lower in the stand, the photos can't see into the stand, so therefore my prediction of the height of vegetation is going to be very poor. So DAP is very good for seeing the top of the canopy, but we have shown that if you compare DAP to LiDAR in an enhanced forest inventory, if you were doing a drone-based inventory, your predictions are still very, very good. So you don't have to always see the ground, but you do need to be able to have a map of the ground from LiDAR, for example, to give you the heights. But once you have the heights, you can use what you get from photogrammetry to go away and make predictions. So where do I think drones are useful? I think drones should be useful for pre-harvest assessment, excellent for flying your stand before you want to harvest it, very good for looking at riparian zones, very good for looking at rare and endangered species plant species that might be on the block before you want to go away and work. And the other area we think it's very valuable for is regeneration success. So LiDAR is terrible at giving us regeneration because LiDAR can't measure something that's very, very short and close to the ground. For a variety I can talk about, I'm not going to talk about now, but it's a problem. So LiDAR can't see very short vegetation. So regeneration surveys are hard for LiDAR because we can't count how high the trees are. But drones can. So drones will give us a three-dimensional point cloud. Even if the point cloud is this high above the ground, we will still get a very accurate point cloud. And we get the imagery. So we have blue, green, red, and the point clouds that we can actually bring together to go away and map regeneration. So in British Columbia, it's expensive to do regeneration surveys. You've got to put a helicopter, you need people to go away and do it. If we could fly the drone over small areas, look at the imagery, and also look at the point cloud, we get some extraordinary estimates that we get back. So here's just our 3 test sites. We fly the drone. Every single part of the landscape then, we have our imagery. We then segment that automatically. We can classify it as the species we want, the ground or bare, or the species we want, other vegetation like weeds or bare ground. We can do that classification automatically and then go and classify the whole block in terms of regeneration success. In this case, it's conifer deciduous, which we would regard as a weed, and then the ground. So this would be our map of our regenerating stand. We get proportions for every stand, so we know how well it's coming back. We do this at 5 years, 10 years, 15 years, 20 years. But because we have the heights, we also know the height. So how high the vegetation is in terms of how it's growing. So a very useful application of how you can go away and use drones. Another very cool application is fire, assessing the damage after fire. This is our 2017 fires in British Columbia, our worst fire season on record, the largest fire ever in British Columbian recorded history. This is a drone over one of the patches of fire. Again, you can see the extraordinary detail that we can get back. Allows us to look at things like burn severity, how did the fire burn, where didn't it burn, the effect of crowns and so on. Extraordinary data that we can go away and use. Has its place. We're not going to map every single fire in British Columbia. We're not going to map all the fires in the Boreal. We're not going to do all the regeneration in the Boreal, but you can use these technologies in targeted ways to help inform the decisions that we make. We're undergoing a revolution. We have a democratization of space. You can go and fly a drone. You can go and even invest in a shoebox satellite and put it up with Google for $100. The Indian Space Agency launched 150 microsatellites into space 3 weeks ago. It was the largest ever satellite launch of lots of satellites at one time. So we're seeing this massive democratization of space, be it drones, be it these very cheap iPhone cameras we have in space, even if it's just building your own phonology camera. People can do these things now. We couldn't have done that 10 years ago. You can go and buy a Raspberry Pi. You can go down a Radio Shack and build yourself a remote sensor. You can put a remote sensing thing on your iPhone and go and do a study. Imagery has become much more available. The idea of a company or a country not providing its data free anymore is seen as an anathema. The Europeans with the Sentinel program have been forced to think of it all as free because of what the USGS did with Landsat. It's revolutionizing the way we think about data, and I think it's going to get bigger and bigger and bigger and bigger. Eventually people are going to say, it's unacceptable for you to fly LiDAR and not make it publicly available. So we're moving towards democratization of space and democratization of imagery. We also have inquisitive students, thank God. We have big data, we have computers that can go away and process stuff more than we've ever had before, and that computing is relatively cheap. And I would argue that some of the most desperate questions we have at the moment really need students working on them and finding solutions. So with that, thanks for your time. I hope I've given you a sense of the way I think it's going and stuff that we're doing at UBC. Thank you very much.